Assalamualaikum warahmatullahi wabarakatuh. We have come to chapter 6, chemical equilibrium. Today we are going to learn about dynamic equilibrium. What is dynamic equilibrium, reversible reaction, and the law of mass action? We need to state the characteristics of a system at equilibrium and explain the features of a graph of concentration against time and rate versus time for a reversible reaction. Dynamic equilibrium describes a condition when a reaction keeps changing yet it's finely balanced. Balance is a creation of Allah for nature. In nature, the fundamental law proves that matter moves towards a stable equilibrium. The Quran, through Surah An-Naba, summarizes the creation of mountains and how they stabilizes the nature. In 2003, Zakhlul An-Nagar, in Geological Concept of Mountains in Quran, has explained the existence of mountains in the isostatic equilibrium of the earth. He began by quoting verse 53 of Surah Al-Fussilat. We will show them our signs in the horizons and within themselves until it becomes clear to them that it is the truth. But is it not sufficient concerning your Lord that He is over all things a witness? Let's look at what we mean by reversible reaction. Few chemical reactions proceed in only one direction. For example, when you have A and B as reactant, you're going to have C and D as product. Example 6.1, you have methane plus chlorine gas. You will have chloromethane and hydrochlorine gas. The reaction occurs in UV light. But most chemical reactions are reversible, at least to some extent. For example, when you have A, it's going to become B. And when it becomes B, it's going to go back to A. This is what we call reversible reaction. Meaning that reversible reaction can go in both directions, for example, from reactant A to become product B, or from product B to become reactant A. We are going to use certain terms. Forward reaction is the reaction proceeding from left to right. Backward reaction is reaction proceeding from right to left. Reversible reactions are the reactions which take place in both forward and reverse directions. This is the arrow indicates reversible reaction. As we know, reversible reaction can go in both directions. When molecule products are formed, the reverse process begins to take place and reactants are then will be formed from the products. To understand this further, let's discuss example 6.2, the dynamic equilibrium between sulfur dioxide and sulfur trioxide. The net concentration of SO2, O2, and SO3 do not change. SO2 and O2 combine to form SO3 at the same time SO3 decomposed to form SO2 and O2. Non-reversible reactions proceed in only one direction. The reaction proceeds toward the formation of product, and once it's formed, the process comes to an end. Example, the decomposition of hydrogen peroxide to water and oxygen gas. So, what is equilibrium? Let's talk about heat as an energy flowing from high temperature object to low temperature object. When we have two objects at the same temperature, there will be no net flow of energy or heat. That is why a covered cup of coffee will not be colder than or warmer than the room temperature where it has been in for a few hours. This phenomenon is known as equilibrium. In Chapter 1, we have learned how to calculate the percentage yield for certain non-reversible reactions. But in real life, chemical reactions may not be as complete as that. For example, the following reaction is far from completion. It's impossible to have pure NO2 or N2O4. However, in a closed system, the ratio of product over reactant, concentration of N2O4 over concentration of NO2 to the power of 2 is a constant. We call it equilibrium constant Kc. This phenomenon is known as chemical equilibrium. Such law is known as the law of mass action or mass action law. When conditions such as pressure and temperature change are met, a period of time is required for the system to establish equilibrium. A system is said to be in dynamic equilibrium when a forward and reverse reaction proceed at equal rates and the concentrations of reactants and products remain constant over time. Let's look at a graph showing concentration against time for reversible reaction. At time equals to 0, we can see that A and B, the reactants, are at the maximum concentration, and C and D, the products, is 0. The concentration of C and D increase with the increasing of time, and in contrast, the concentration of A and B decrease. Up to a certain point TA, both reactions have no further change in the concentration of products and reactants. Another graph is the graph of rate versus time. After TA, the rate of forward reaction is equals to the rate of reverse reaction. There is one point that is important here. Let's say we have a balance equation N2O4 becomes 2NO2 in a reverse reaction. At equilibrium, the rate of the forward reaction is the same as the rate of reverse reaction. Therefore, the concentration of N2O4 and NO2 remains constant, but it is not having the same molarity. Thank you very much for watching, and now let's proceed to equilibrium constant.